Good evening, Fiveable. My name is Shane Durkin, and I will be hosting AP Stats videos all year long to make sure that we're helping you out with getting a 5 on the AP exam. Today we're going to focus on normal distributions. Normal distribution is going to be one of those things that's super important for us to understand conceptually moving forward in our statistical careers. It's going to come up again in inference, in hypothesis testing, so we really want to make sure that you're asking questions. Here's kind of the agenda for our stream. Quick little intro. We're going to describe and apply the empirical rule, which is the 68, 95, 99.7 rule. We're going to describe the standard normal distribution. That's going to be super important moving forward. And as always, perform those actual calculations. And then at the very end, determine how do we assess if something is normal or not. So we want to be able to determine if something is in fact normal so that we can run the calculations. All right, so here's some important information about normal distributions. First, all normal curves are symmetrical, single-peaked, and bell-shaped. Okay, like here, we have two normal distributions. Some are wider than others, but they're all characterized or described by the average and the standard deviation. So all are described by the average, which is going to be in the middle, and the standard deviation. So here we have two normal curves. They're both normal. One has a larger standard deviation or a larger spread, but they're still approximately normal. Again, these two curves show normal distributions with an average and a standard deviation. We abbreviate normal distribution, so you're going to see this notation a lot. Stats is really big on its notation, so you're going to see notation a lot as up here. So this right here represents a normal distribution centered at this number with a spread of, or I should say a standard deviation of this number. So you're going to see that, and that's going to indicate to you, hey, this is a normal distribution centered at whatever the first number is with a standard deviation of whatever the second number is, okay? Any particular normal distribution is completely specified by two numbers, its mean and standard deviation. So once again, those are going to be the two most important things moving forward with a normal curve. And the mean of a symmetrical distribution is at the center. We talked about that last stream. But the average is going to be right at the middle of our distribution. The standard deviation, now we can sort of estimate standard deviation based off a normal curve. It's essentially where the change of curvature occurs. So it's when it stops becoming concave down and starts becoming concave up. So that's how you can kind of estimate where your standard deviation is. So on our standard deviations here, we can kind of see this curve is going down, and all of a sudden it now opens upward. And the same is true regardless of how skinny it is. Why are normal distributions useful? Well, they're useful for a couple different things. One, normal distributions are good descriptions for some distributions of real data. We as statisticians love to look at real data, and a lot of real data can be described by a normal distribution. Normal distributions are good approximations of the results of many kinds of chance outcomes. So anytime you think about a chance outcome, normal distributions are usually good models for that. Like, what do we do? Picking names out of a hat. Let's say you have 20 people, 5 identify as female, 15 identify as male, and you want to know what's the probability or what's the distribution of picks. Like, do I get 3 females or 5 or 10? You can see that with a normal distribution. And then many statistical inferences are based on normal distributions. That's going to come around later when we work with hypothesis testing and confidence intervals. All those normal distributions going to pop in. So let's start talking about. Let me see if I can move. Looks like I'm blocking some of the work. Let's see. All right, we'll just keep it. I will walk you through that part that I'm blocking on the bottom left-hand corner. But the empirical rule is pretty simple. If we have a normal distribution with an average at mu and a standard deviation of some number, if we go out one standard deviation in both directions, so we go above 1 and below 1, we're going to cover about 68% of the data. That's if our distribution is normal. So we have to have a normal distribution in order for that to work. If we go out another standard deviation, so 2 standard deviations in each direction, we're going to cover 95% of the observations. And if we go out one more, we're essentially covering all observations. We're covering 99.7 of observations if we go out 3 standard deviations. Let me show you a picture to help you out. So here's a great picture to show how our data is distributed in a normal distribution. So if I go out 1 standard deviation, here's my center. If I go out 1 standard deviation above, 1 below, I'm covering 68% of the data. If I go out another standard deviation, I'm covering 95. And 1 more gets me to 99.7. So you can see here on the tail, very, very little data falls outside of 3 standard deviations. Let's try this. So the distribution of California Test of Basic Skills, CTBS, vocabulary scores for 7th grade students in Oakland is pretty normal. Suppose the distribution is, here's that notation again, oops, n parentheses 6.84, comma, 1.55, and the range is between 0 and 2. Here's a sketch of that distribution. Notice the center, 6.84. Notice if I go out, whoops, 1 standard deviation, I'm at 6.84 plus 1.55. If I go out another standard deviation, again, I'm adding the standard deviation to the average. And so that would be a rough sketch of this distribution. Anytime on the AP exam they talk about normal distributions, you're going to want to draw a sketch of it. And we'll come to that, the steps to solving these in a little bit. But you're always going to want to draw it out just to give yourself a mental image of what you're actually working with. You're always going to want to label to make sure that you're getting full credit. So let's say I wanted to use the empirical rule to figure out what percent of scores are less than 3.74. So if you notice on our curve, 3.74 is going to be 2 standard deviations below the average. So 2 full standard deviations below the average. Anytime that we can get full z-scores, so integer z-scores, so like 1, 2, -1, -2, we can use empirical rule to answer a question like this. What percent of scores are less than 3.74? So let's see what that would look like. So we're going to go to 3.74, and we're looking for scores less than. So that's going to be everything below that number. Since we know about 95% of the data falls in between 2 standard deviations, so in red, we know 95% of the data falls between there. That means there's 5% of the data that's in our tails. So there's 5% in both of these added together. So that means there's 2.5 in each of the tails. So each of the tails represents 2.5, which means if I'm looking for anything less than 3.74, it's going to be about 2.5%. Might not be exact, but it's around 2.5%. What if I wanted to know the proportion that falls between 5.29 and 9.94? Again, we can use the empirical rule here because we're using full standard deviations. So 5.29 is 1 standard deviation below. 9.94 is 2 standard deviations above. So I know if I go out 1 standard deviation, I'm covering that 68%, which is right there. And if I go out another standard deviation, I'm covering 95%. Now take a look at this math on the right. 95, which is this whole area, 2 standard deviations out, minus 68 is going to give me just the area right here and right here. Here and here, which is about 27%. So divide that by 2 to get one side of that, and then I'll add it to the 68. Whoops. So between 5.29 and 9.94 is going to be that 68 from the center plus the extra 13.5 on the side. All right, so why do we standardize? A couple different reasons. There are so many normal distributions with unique standard deviations and averages. So in order to compare normal distributions, we standardize it. It allows us to compare apples to, should be oranges, but it allows us to compare different items. Think about the SAT and ACT. Some students take the SAT, some students take the ACT. Just depends on which one you feel that you're better at. If I'm a college and I get 2 applicants, one scored a 27 on the ACT, and one scored a 1400 on the SAT, how do I know who did better? Well, that's where standardization comes into play. So we can standardize it, and then we can see, all right, who did better respectively to their peers? Who's further above the average? And that will tell me who did better. So we standardize a lot to help us compare. In order to compare, we have to transfer everything to what's called the standard normal distribution. All normal distributions are the same if we measure in units of size, whatever the standard deviation is, from the mu as the center. So the standard normal distribution is the normal distribution with an average at 0 and a standard deviation of 1. So again, if we went out 1 standard deviation here, we're covering 68% of the data. If I go to another standard deviation, I'm covering 95 and one more, 99.7. How do we standardize a variable? So we have this SAT score, or we have this vocab score. How do I standardize it? Well, the first thing you're going to do is draw and label a normal curve with the mean and standard deviation. Then you're going to calculate what's called a z-score. So z-score is super, super important, and we got to know why. So here's the formula on the right. Z equals your data value, x, or your variable, minus mu, which is always your mean or your average, divided by the standard deviation, which is always going to be how the average distance every point is from the average. Once you get your z-score, you're going to go to a chart to see the p-value in the table. So the p-value in the table is going to tell you the probability that that happens or anything below it. Again, we're going to do an example in a minute, but I do want to stress the importance of what it means. And then always in stats, we want to conclude in context. If you're not putting context into your free response questions, you're going to get some points off. So we really want to make sure that we get in the habit of putting context into all of our questions. And it's really easy to do. I'll show you. So for example, we go from our non-standard normal curve, which has an average of whatever the mu is, and a standard deviation of whatever, and we change it over to a standard normal curve, where our new average is 0, and our new standard deviation is just 1. Oh, wrong one. Here we go. Okay, so here is the standard normal table. That's going to be important for us to figure out the probability that something occurs. So because all normal distributions are the same when we standardize, we can find area under any normal curve from a single table. The standard normal table is the table of area under the standard normal curve. The table entry for each value z is the area under the curve to the left. So it's always going to give you area to the left. And that area is called p-value. That's going to be so important when we do hypothesis testing. Going to be really, really important when we do hypothesis testing. So I want to make sure that you're understanding what's going on here. P-value represents the area or the probability of that or below happening. And it's usually probability or percents. Let's give it a shot. So here's what your t-table or standard normal table will look like. It'll have your z-scores on the left and on top. So if you notice, the left is going to be the ones and the tens. The top is going to be the hundredths, right? So if I was looking for negative 2.51, it would be this number right here. Sorry, this number right here, 2.51, negative 2.51. If I was looking for negative 2.19, I would go to negative 2.1 and then go all the way to 9. If I wanted to get a p-value for a z-score of negative 2.33, where would I look? Well, I would go to negative 2.3 and then go all the way to the 3. So I'd have a p-value of about 1% or 0.0099, which if we converted that to a percent would be 0.9% or 0.99%. Okay, so here I have some standard normal curves, or some z-scores that I want us to convert to p-values, and then p-values to z-scores. I have to do a couple changes so I can get my document camera up and running. So give me 30 seconds. Hang on. All right, I'm back. So let's share a new screen so that we can practice. If you have your normal tables out, go ahead and grab them. They're going to be important for us. How do I? Let me do this. All right, here's our standard normal table. First one, we wanted to find a z-score of negative 2.23. So I'm going to go to my negative side, 2.33 or 2.23. 2.2, and I'm going to go all the way over to 3. I'm going to make this a little bigger. So my z-score is negative 2.23, which gives me about 1.28%. So that percent right there is the area to the left of that z-score. Let's go back. 1.65. So again, I'm going to go to my z-table. These are all negatives. My next part is going to have the positives, 1.65. So 1.6. And then I go to the top to find out where 5 is. Well, there's 5, so I go over until I hit the 5. So right there, 95% of my data is at or below a z-score of 1.65. Let's try another one. 0.52, so just above the average. I'm going to look on my second sheet. There's 0.5, and there's 0.52. So 69.8% of my data falls at or below 0.52. Let's take a look at our last one. So now I'm giving you the p-value. So what would the z-score be if our p-value was 0.79? Well, now let's go to our table. 0.7, here's 0.77, here's 0.79, 0.79, 0.791. So we have to decide between these two which one's closer. It looks like this one's going to be a little bit closer. So a z-score of 0.81 would be the closest z-score to a percentile of 79. So we're kind of going backwards. And let's go backwards one more time, 0.23. So I want to know what z-score would get me 23% of the data at or below it. So going over here, I'm going to have to go to the negatives because that gives me everything below the mean, which the mean is the 50th percentile in this case because the mean and the median are the same. So what was it? 0.23. So here's a common mistake I see. Students will go for maybe this one right here, 0.23, but we're looking for 23%. So be very careful when you're doing that. 23% falls. It looks like this is going to be our closest. 2. Yep. So it's going to be 0.74. 0.74. Let's check our answers. There we go. Looks good. So that's how you go from z-score to p-value and back and forth. All right, let's try some examples. In the 2008 Wimbledon tennis tournament, Rafael Nadal averaged 115 miles per hour on his first serves. Assume that the distribution of his first serve speeds is normal with an average of 115 and a standard deviation of 6.2. About what proportion of his first serves would you expect to be less than 120? So what proportion of his serves are going to be at or 120? So first thing we want to do is draw and label a normal curve. So if I had paper and pen, I would draw and label. I guess I could do it right here. Let's give it a shot. So we're taking our normal curve. We're drawing it. We have an average of 115 with a standard deviation of 6.2. And then, looks like you can't see it too bad. I would draw a line at 120 and shade everything below it because I'm trying to find that or below. And then we'd calculate a z-score. So again, here's the formula for z-score. X is the variable or the number that you're looking for. Mu is the average, and S is the standard deviation. So I have a standard deviation of a z-score of 0.81. I would then take that and find the area below that value using my. So I go to 8.8 and then 1, and it looks like it's going to be right here. Oops. At 79.1%. So 79% of his serves are going to be 120 or less. Let's try another one. Oh, and then always state it in context. I'm sorry. So we expect that 79.1% of Nadal's first serves will be less than 120. We expect 20.9% of his serves to be greater than 120. How do we get that? Well, if about 80% of his serves are going to be less, that leaves 20% that have to be more. So we essentially did 1 minus the probability that he did serve less than 120 to get the probability that he will serve more than 120. Tiger Woods hits his driver a distance the ball travels can be described as a normal distribution with an average. Remember, this is how we read this, a normal distribution, so it's symmetrical, with an average of 340 and a standard deviation of 8. What percent of his drives are between 305 and 325? Well, first thing we're going to do is we're going to draw it out. So notice I drew my average. I labeled the center. I wanted to know, hey, between 305 and 325, this is going to be important because you sometimes won't get credit on the AP exam if you don't draw it out. So make sure you're drawing these out and labeling. So when I got my z-score for 325, I got 2.63. My z-score for 305 was 1.3. My next step is to then look up the p-value using my standard normal table. So p-value for 2.63 is 0.9957. The p-value for 0.13 gives me an area of 0.5517. So to get everything in between, I'm going to take the top one, 0.9957, and subtract it from the bottom one, 0.5571, to get everything in the middle, which is 0.4440. So that's an important distinction when you're trying to find in between two numbers. You take the top probability, subtract it from the bottom probability to get the in between. Any questions? Alan, how you doing over there? Just want to check in to make sure. Again, this goes a lot better and you take a lot more out of it when we're able to ask questions, engage. Whenever you're stuck, just let me know. Is this something you're currently working on? Have you done it in the past? Let me know. And then always at the end, state it in context. What are we talking about here? About 44% of Tiger's drives travel between 305 and 325. Great. Had a test on it last week. How'd you do? And did you use the calculator? So here's a little trick for the calculator. I use TI-84s in my classroom, not the Nspires. So if you're using the Nspires, just send me an email and I can get it to you, get you those definitions. But for the most part, I think everyone's using the TI-84s. We can get quick results using the calculator. And Alan, you probably know this since you already took the test. However, NormalCDF, yeah. So NormalCDF, do you have a TI-84 or do you use the Nspire? Cool. I love it. Those ones are easier to me than the Nspires. So NormalCDF is going to be the probability of obtaining between two values. So that problem that we just did, we can use it on the calculator and get it really quickly. But there is something you need to know about using the calculator on the AP exam that I'll tell you in a little bit. An example of this would be what % of students scored between 70 and 95 on the test. We could use the calculator to get that probability very, very quick. Now you still want to draw it out, but we can use the calculator. Normal PDF, we really don't use that often. However, you could get the probability that you get that exact number. Again, we really don't use it very often, but it's there. And inverse norm is going to be super valuable. It gives you the actual score for the area that you want. Let me say that again, or I'll say it according to my notes. It gives you the X value given the probability or the percentile. So let's say you scored 92 on a test. You wanted to know what proportion of students did you score better than. You could get that using inverse norm. Here's how you do it using the calculator. So you're going to go NormalCDF, again, gets you the area under the curve between 2 points. You're going to hit the button that says second. So I'll take out my calculator. The button that says second is going to be at the top right-hand corner in blue or yellow. Hit that button. Then you're going to hit vars, which is right below the down button. You're going to scroll down to number 2 to select NormalCDF. And then you're going to enter the following information. First is the lower bound. So this is the lowest number that you want. Now, if you're just saying, I want everything below a certain value, I would suggest putting a large, small number. That's weird to say. But you're going to put a very small number, which negative 9999999 is going to work. And then you're going to put the upper value. So again, if it's something that you want to find everything above a certain value, you're going to want to put a very large number like 99999. After that comes the average and comes the standard deviation. Hit enter twice and it'll generate your response. Okay, so let's say I wanted to know the value of, or the proportion of students that scored between 70 and 95 on an exam. That students averaged an 82 with a standard deviation of 7. So I'm going here. My low is going to be 70. My high or upper is going to be 95. My standard deviation is, I think I said 82. Sorry, my mean is 82 with a standard deviation of 7. Enter once, enter twice. That's going to give me the probability that students scored between those two numbers. Normal CDF. A lot quicker than this. However, if you're using this on the AP exam, especially on free response questions, you're going to want to label everything. So when you type that into your calculator, write it on the test and label all these numbers. Lower bound, upper bound, average, standard deviation. If you do not label, you will not get full credit on the AP exam. Make sure you're labeling. They're really pushing in these later years to get away from calculator talk. They're trying to get students to avoid using the calculator for their responses because they want to know if you conceptually understand it. And the calculator, because so many different universities use different statistical programs, they don't really like using calculator notation. Inverse norm is going to be very, very similar. It's just going to get the value that is associated with that percentile. So again, you're going to hit second vars, select number 3, inverse norm. This time you're going to start with the area. So let's say I want to know 52%, the bottom 52%. I would put 0.52. Then you put the average, standard deviation, hit enter. Very, very similar for inverse norm. When can we use normal calculations? So we can use normal calculations. We're transitioning to our last part of our time together. We can use normal calculations whenever something is normal. If it's not normal, we can't use normal calculations. We can assess normality in a few different ways. We can assess normality by plotting the data. So using your graphing calculator, type in all the numbers, graph it, see what it looks like. If it's normal or approximately normal, then we can use normal calculations. You can also use the 68, 95, 99.7 rule, also known as the empirical rule, to check to see if your distribution is normal. If 68% of your data falls within 1 standard deviation, 95 falls within 2, 97 or 99.7 falls within 3, you have approximately normal data. And last but not least, you can construct a normal probability plot, which I'll talk more about that now. A normal probability plot, we don't see very often, but they do like to throw these in every now and then. So it is good to know. So these plots are constructed by plotting each observation in the data against its corresponding percentile z-score. So your percentile and your z-score are plotted along with your score. So we can see from this histogram that our distribution is not normal. Over here, we see our probability plot. If it's not linear, it's not normal. So if it's non-linear, it's non-normal. This is not linear at all. These do not line up in a straight line. So this is not linear, which means I can't use normal calculations. If something is linear, it'll look more like this. So how do we interpret these probability plots? If the points on a normal probability plot lie close to a straight line, the plot indicates that the data are in fact normal. Systematic deviation from a straight line indicates a non-normal distribution. We just saw that. That is not normal. We cannot draw a straight line through all those points. This, we can, right? It's roughly normal. Outliers appear as points that are far away from the overall pattern. So see this point over here? That could be a potential outlier. All right, y'all, that is our time for tonight on normal calculations. The best way to get better at this is just to practice. And I'm thinking we'll go back to normal calculations throughout the school year to make sure that we continue to practice this so that you guys feel very, very confident in it moving forward. Please go ahead and follow us on Twitter, Instagram, and YouTube. we're really trying to get a building for AP Stats so we could figure out where you are. And instead of you getting this material at the end of your test, Alan, we really want to present it where you're going in the middle. So I'd love to hear what you're learning now. It might be linear regression. And that's what we're going to stream in the next coming weeks. So we're really hoping to build a following. Tell your friends, tell whoever, tell your teacher, hey, check out this guy streaming on Fiveable for AP Stats. Really trying to build a following here so we can catch up with all those other Fiveables that are crushing it. Okay, you're on designing studies and experiments. We did that in the beginning because some, and I would say maybe even most stats teachers do that in the beginning, but that's good to know. We have videos on that, but maybe we will restream them. Yeah, I know Jerry did some videos on that, so definitely check the replays for that. Thank you again, Alan, for staying with us this whole time. Appreciate you. Check out Fiveable on Instagram and Twitter to tweet us what you want content on. If you're like, hey, we love the practice, let's get some more practice in there, we'll do the practice. If you don't think you need the content slides, we can jump right into practice. Maybe do some AP problems, all that jazz. Thank you for your time. If you have any questions, Alan, even if it's on sampling and experiments, I'll stick around for a minute to answer them. Absolutely. Let me see if I actually have a slide on that. Hang on. Ooh, I think I might have a slide on it. Let's see. There we are. There we go. Borrow this from my friend Jerry, but here is blocking. So blocking is going to be very similar to stratified sampling. The only difference is stratified sampling. Stratified's for sampling, blocking is for experiments. Let's get, here we go. Okay, so if we think that some characteristic is going to influence how people respond in our experiment, we want to block by that characteristic. So blocks help us reduce variability in response, and it allows us to compare a lot easier. For example, if I was testing a drug on dogs, like a painkiller drug, I might think that the breed of a dog will have an influence on how that dog responds to the drug. So what I might do is block based off of breed of dog, and then within those breeds of dogs, within those blocks, I'm going to run the experiment. It allows me to compare and remove the variable of breed in measuring the response variable. So let's say here's a good image. I have my units, let's say they're dogs. I block them by Huskies and Shih Tzus. Then within those, I randomly assign them to the first painkiller and the second painkiller. First painkiller, the second painkiller. And then I compare. So how did Shih Tzus take this drug versus, or how did Shih Tzus in this section, how did they compare across the treatment? And then I can go separately to the other one, how did they compare? How did the Huskies compare? So it removes a variable that could affect how the subjects or the units respond to the treatment. Experimental units are randomly assigned to treatment groups after a non-random grouping. So it's important here to know that blocks happen after, randomly assignment happens after we block. And blocks share a common characteristic that will impact the response. How's that feel? Some common ways that we block. So on the AP exam, they may have you carry out an experiment. So you may have to describe something like what you see here. They also might just have you say, here is an experiment we're running. Explain one characteristic you might block off. So it really depends on the question from year to year, but sometimes you will have to carry out an experiment. Sometimes you'll have to justify why you would block the way you did. And really the explanation is always going to be some characteristic is going to impact your response variable. So just knowing that is going to get you credit on all the questions, right? You're always blocking because you think it's going to have an impact on the response variable. If I didn't block, then I might see that, or I might give all the Shih Tzus the painkiller and all the Huskies not, in which case that will mess up my results when I compare, because maybe the size of the dog is actually influencing how they are receiving the painkiller. Multiple choice, you're never going to have to run an experiment. Multiple choice, it's going to be more conceptual. Like, why would they block based, or what would you block off based off of this situation? Let's see if Jerry has anything else. Match pair. Students get match pair mixed up a lot as well. Match pair is when you pair experimental units based off of commonality, and then you run your experiment. We must have multiple pairs to ensure replication, one of the key features of a good design. The second type of match pairs is that both every experimental treatment gets both treatments. So like the famous example is if I'm testing out to see if boots, there's a certain spray that is waterproof on my boots. So I'm one experimental unit, but I get both treatments. I get one boot with the spray, one boot without the spray. And so that allows me to eliminate the confounding variable of what I do for a living. Because maybe I'm going to use my boots more inside than my dad, who's a carpenter, who's going to be using his boots outside. So we want to eliminate that. Dominant versus non-dominant hand, great example. I hope that helped. I will stick around if you have any other questions.
Hello. Go home.
Hello. Our custodial staff just came in. That might be my cue to leave. Thank you, Alan. Please feel free to shoot me questions. You can take my email down. It's just my first name dot my last name at ousd.org. Happy to help. Have a great evening. Thank you. Super, super good. Please give me feedback too. Always looking to improve. Thanks and have a great evening.